All right. Hi, everyone. Hello. Hi. Hi there. How are you doing? Doing okay? Making it. Last week was hard. This week is also going to be pretty hard. So I just wanted to jump in today. We're going to be talking about linky listies. And in particular, we're going to break it down this way. We're going to first give us a quick recap of what we learned from last lecture, which was how we could treat the sequence as an abstraction. It's like the list that we saw from last lecture. And linked lists are going to be one way of implementing that sequence abstraction. And at the very end, we'll talk about some examples to give you some intuition for why we might care about linked lists. All right, so announcements. Tomorrow's a holiday, so there's no class. If you happen to have time, I think it's really cool if you could go to a high place, like maybe go to the Berkeley Marina or go up the fire trails, and you can go watch the fireworks. It's gonna be pretty cool. So there's no class. What you can do is if you have a Tuesday morning lab, a lab that would normally meet tomorrow, you can still attend lab today, or you could go to Mitash's special lab on Wednesday morning. You can submit at home, or you can use a lab drop, which means you just don't submit any lab, and totally fine as well. There are also going to be no Wednesday morning discussions, and again, Mitash has a lab in place of his discussion that Wednesday morning. So kind of because of this holiday, we're not going to have discussion, and because of that, no quiz either. So your next discussion and quiz will be on Thursday. Homework 3 is due Wednesday. You've had some time to get started on it, and if you haven't gotten started on it, it's still fine. You have plenty of time. You can go to office hours today or office hours on Wednesday. Homework 4 is released today, and it's due Friday. Make sure you get started on it. And it's the last homework before the midterm. I think these two most recent homeworks are really important it's really important that you master homework 3 and homework 4 for the exam. So definitely make sure you spend some extra time with it, really understand what's going on. If you don't finish it, that's fine too. Homeworks are graded on effort, but I really strongly recommend that you take a serious look at that homework and really try to understand what it's getting at. MAPS is released today, and it's due next Tuesday. So you have a little bit of time between homework 4 and MAPS if you finish it as well. But as always, it's really important that you start early with these projects. MAPS, like Hog, is also solo, but from what I've heard from students, it's a little bit easier than Hog. So it's less debugging involved, and so maybe you'll get through it a little bit quicker. And one last thing is if you find yourself waiting a long time in office hours, you can also ask other questions in lab as well. So lab is a place where you can ask questions about lab, but you can also ask questions about homework and project as well. But priority will be given to lab questions. But feel free to, if you're already in lab, just go ahead and ask other questions. Any questions about the announcements, about what's going on this week? All right, cool. Jumping into content. So this week we're talking about data. And so the goals for this week are to continue our journey through abstraction with data abstraction that we introduced last week. And the way we're going to do that is we're going to study what we call abstract data types, right? And we create those data types using data abstraction. And so one data type we've been talking about is called the sequence abstract data type. And just to recap again, data abstraction lets us treat compound values as individual units, as whole units. And so what that looks like is I have compound values that we describe in terms of how they're manipulated. When we say we have a list, for example, we talk about what we can do with that list rather than how it works. Because the way the list is represented in Python, it has some special magic, but we don't really care about how that's represented. We just say I can index with lists, I can get slices from lists, I can add lists together. So this is kind of the separation, and we call that separation an abstraction barrier. So you can think of it visually. I have the behavior, which is above the abstraction barrier. This is how I use a list. And below the abstraction barrier is how that list is implemented in Python, which we don't know and we don't care about. The way we cross this abstraction barrier, the way we the way we essentially bind, the way we manipulate information with the way it's represented is using what's called constructors and selectors. So we can construct lists using that bracket notation. We can get information out of lists using also the bracket notation, except with giving it an index. And so that's how we interact. That's how we get behavior. We get behavior by crossing this bridge using constructors and selectors. All right. And to talk about sequences in particular, there isn't just one sequence class or data abstraction. I've been talking about lists this whole time, but that's only one implementation. So the sequence abstraction is a collection of behaviors. It tells us what we want to do rather than how we do it. And so the behaviors in particular, I've already kind of mentioned them. We have two that I want to focus on for today. We have length, which tells us maybe how long that sequence is. And we also have element selection, which lets us say, I want to get this item here at index, for example, 2. And in Python, we've already seen two versions of sequence abstraction. We've seen lists, and strings are also sequences as well. So you can do a lot of things with strings just the same way with lists. I can index into them. I can select ranges and whatnot. So I'll give you a quick demo later. So we can use built-in syntax like that to do that. So let me show you a demonstration. Okay. All right, so I have Python 3 open up here. And what I'm going to do is I can create a new list of odd numbers. So I can say 41, 43, 45, 47, 47, 49, 51, 53. So that's a list of odd numbers. And because this is an assignment statement, Python shouldn't print anything. Cool. What I can do is I can take the length of this sequence, and calling length on this sequence will give us some kind of number, which tells us how long this sequence is. So this sequence has 7 elements. I can also index into the sequence. And this will get not the first one, but the second one, because Python and computers are kind of weird. We start counting from 0. So the 0th index is 41. The 1st index is 43. So Python says 43. We can perform computations. I can say I can combine the number 41. I can multiply that with the number 0, 1, 2, 3, 4, 49. I can, 49. I can add some extra stuff. I can add the length of the odds, and maybe I can add 1. I'll get 2017. No off by 1 error this time. All right. And lastly, we can still do that indexing notation, except one thing I think you haven't seen yet is you can put an expression for the index. So I can say, I want to select, let me type this all out first and we'll talk about it. So what this is saying is I want to select from odds this value, this index. And that index is given by the expression odds of 3 minus odds at 2. So odds at index 3 is 0, 1, 2, 3, 47 minus 45. So it's like I say this is equivalent to saying I want odds at index 2. So I should get 45. There we go. And we've also seen how we can use strings. So I can say CS61A is pretty fun, so let's put CS61A in the name fun. We can get the length of that string, which is 5 characters long. I can index into a string. So that should get me the character C, because that's at index 0 of that sequence. And I can also take ranges as well. So I can say fun. I want to get the range from length of pi onwards. So we can do the same thing that we saw with indexing with slicing as well, where we can put any arbitrary expression that evaluates to a number and use that as our start and end points. So here we're saying I want to get a slice of fun from the length of pi, which is 2 characters long. So it's like saying 2 to the end. So what I should get is 61A. And likewise, I can also slice from the end. Let's say I want to remove 61A and just get CS. An easy way to do that is by using the negative length of the part that I want, or the part I want to get rid of. So what this is saying is, let me slice fun from the beginning, starting at 0, which is by default 0, right? And going all the way, but not up to that position. So the length of 61A is 3, so it's like I'm saying from 0 to -3, and -3 just says count backwards from the end, -3 steps. And so I get just CS. So you can slice from the beginning, you can slice from the end, you can get some middle slice as we saw in last lecture as well. Any questions about this demo? You want me to show you something new? Yeah.
So when I remove the minus character from that, what can I get?
Right, great question. What's your name?
Logic.
Yeah, Algin asked the question, what happens if I do this, length of 61A, right? So if I don't have the minus, what this evaluates to is I start from 0, and I go to 3. So 3, I should get 3 characters out, and that'll be CS6. Great question. Yeah.
Why isn't it exclusive? Why isn't it just the first 2 then?
Okay, so what's your name?
Sam.
Yeah, so Sam asked the question, why isn't it just the first 2? So if you think about it this way, let me type out my string. So my original string fun is still CS61A. So the way I wanted you to think about indices is like this. It's like here at the very beginning where my cursor is right now, that's like index 0, right before the C, right? And then here, right between the C and the S is like position 1. Position 2 is between S and 6, and position 3 is between 6 and 1. So to get any slice, this is a really useful trick. To get any slice, I can just say, let's start from 0 and go 0, 1, 2, 3. And so because the way we define this slice is like saying the slices are kind of like in between each of those items, this is kind of like an easy way to do that. Maybe I'll post a visual of this online afterwards, because it'll help. Yeah, Sam, follow up.
But in the lecture slides, it says that the upper ranges are exclusive.
Great question. So it is exclusive because what's fun of 3? Because the 0th element is C, first is S, second is 6, and fun of 3 is 1. So it is exclusive, yes. Yeah, so the way you can think about it is like my 6th slice is kind of like there, and the 6th element is immediately after it. You can think about it that way. All right, cool. Okay. So we've seen 2 versions of the sequence abstraction, 2 implementations, the list and the string. And so working with lists, we've seen a couple of these examples. I can create a list containing any arbitrary values. I can get the number of elements using the len function. I can return elements by index, which will give me the number 8. I can concatenate and repeat lists. So here, I'm going to add a list of 2 with whatever I get from digits times 2. Since digits is a list, and the way you can think of multiplication here is then that we just have digits plus digits. That's essentially what digits times 2 means. So we should get a big list. We can also have nested lists. I can put lists within other lists, because lists themselves are also values. So if I want to get that nested list, I can say pairs of 1, which will give me that inside list 20 and 30. Then I can select more information from that list using another set of brackets, because I know pairs of 1 evaluates to this list. So it's like I'm saying this list at index 0 should give me 20. And so that gives me 20. So now I want to talk about linked lists. And linked lists are another way to implement this sequence abstraction. So we've seen plenty of examples just in the last couple minutes of how sequences work. But this linked list idea has a new definition. We have a structure called a link. And a link has 2 parts. The first of which is called first, which is the value for that current link. And the second part of it is the rest, which is the next link in the list, which could also be empty. And linked lists are recursively defined. So I'm going to show you a quick example of how that works. All right. Let's get a new interpreter. So what I'm going to do is I loaded up Python with my files loaded in already. And I can create a link like this, I can assign S to be the link containing 1 as the first, and maybe even 2 as the rest. So this link structure allows us to put anything inside of it. And now I have S, and the way I can get the first out is by saying first of S, which will give me the 1, because that's what I put in for the first. I could say rest of S, and that's what will give me 2, because that's what I put in for the rest. So this kind of goes against the recursive definition. And so the point I want to make about this is that it's easy to make a link that contains 2 elements. But if I want to create something longer that has 3, 4, 5 things, my link definition only allows for first and rest. How do we construct a link that's longer than that? Well, we can compose links. So I can say S is a link of 1, but its rest will not be a number. It's just be another link. So the rest can be a link of 2, and its rest can be a link of 3. And then we can terminate with the empty link, which you just get by typing empty. Okay. Quick note about empty. Empty is not provided. It's only because we've written it in our code somewhere when I imported 09.py. All right. So now if I want to get some numbers from this list, what I can do is I can say first of S should still be 1, because that's where I put the first. But now if I want to get the number 2, I need to do some composition of my function calls. I want to get the first of the rest of the list. Because if we notice here, how this function call unravels, how we execute this function call, is by saying operator is the function first, operand is this call expression. So we have to evaluate the operand, which requires evaluating the operator, which is the rest function, and the operand, which is S. So really the first thing I do is the first call I make is to apply this rest of S call. So rest of S gives us this part, the rest of it. And so then I want to get the first of that rest, which will give me the number 2. And likewise, I can get the number 3 using more nesting. And so I think I'm missing a parenthesis. There we go. I can get the rest, which is this one, the rest, which is this link of 3 and empty, and the first of that link of 3 and empty. And so that's how I work with linked lists. Okay. So just to visualize that, we're going to demonstrate a new way of drawing linked lists. And the way we draw these linked lists is using what's called box and pointer notation. So this is going to be a really important slide. I want you to focus right now. So we say the value of the first is number 1, and we draw that number 1 in a little square, little box. And notice here, for the rest, the value of the rest is an arrow. Sometimes we like to call that a pointer. It's an arrow or a pointer to another link. So notice that inside this box we draw an arrow that points to another link structure. So then I can keep on finishing my recursive definition, which says I have a link of 1, link of 2, link of 3. At the very end, I terminate this link with an empty, which we represent using this box. And so notice that we have the 2 parts. We have a first and a rest. But there is a kind of an interesting detail with this. So I want to point this out. Remember that we said that the value of the rest is an arrow or a pointer to the rest of the linked list? And empty terminates the list. One quick note about this that is kind of important when we talk about linked lists is that we like to think of linked lists in 2 different ways. One way is that we like to think of it in terms of individual links. So an individual link structure is just this box of 2 things. That's an individual link. And that's what Python says. Python can only ever work with an individual link. But sometimes we like to talk about linked lists as entire structures. So you might sometimes hear your TAs or your tutors sometimes saying, the rest of this is a linked list containing 2, 3, and empty. But by Python definitions, that's not technically correct, because really the rest is just a pointer to this link here, which happens to have its rest being a pointer to this link here, which happens to have its rest being a pointer to empty. So I want you to remember, keep in mind that we have these kind of 2 parallel definitions of how to think about linked lists, and just make sure that you're using like the right one in the right scenario. So we oftentimes think of the entire list as a single unit because it helps us reason about programs and helps us write recursive programs. But really the way Python sees it is that we only see a single link at any given time. All right. So the linked list abstraction, I've kind of already shown you how linked lists work. We have a couple functions. I can create a link using the link function, which takes in two arguments, a first and a rest. And we call this function a constructor because it creates a new link structure. Then we also have two functions, first and rest. And what they take in is they accept a link that we call, for example, S, and they're called selectors because what they do is they return the first element of the link and the rest element of the link. And so if a linked list S is constructed from a first element H and a linked list T, then first of S should return that H. This is kind of like by contract. This is how it behaves. First of S returns that H, which is an element of the sequence, and rest of S returns T, which is a linked list. And so to get like the next element, we would say first of rest of S, like I demoed earlier. Questions about what I've shown you about linked lists so far? The definitions, the behavior, the abstraction? Yeah?
So the rest of the linked list is either another linked list or empty.
Yeah, great question. What's your name?
Will.
Yeah, so Will asked the rest of the linked list is either another linked list or empty. Yeah, yes. So the way we define rest, so we go back a little bit, we saw that it's either the next link in the list, it is the next link in the list, which might be empty. Yeah. So it is going to be a link structure. But you can, of course, like we saw before, you can have just like link of 1, 2. But that's what we call something that's not well formed. We won't touch on that too much, but just for now, think of linked list as being this structure where I have a first being my value and the rest being another link. Does that address your question, Will? Okay, cool. All right, so if I show you a quick demo, let's put in a more complicated example. Where's my demo? Let's go to a new Python. And so I started Python again, loaded in my link stuff from 09.py. And here we go. Let's check some stuff. Let's assign March to be link of 1, link of 2, link of 3, 1, link of 1, link of 2, and empty. 1, 2, 3, 4. And so what I've done there is I created a linked list with 1, 2, 1, 2 as the elements. Then I can create another link bound to the name 4 with value link of 1, link of 2, link of 3, link of 4, empty to terminate, 1, 2, 3, 4, parentheses to close. And now I have 4 being bound to the linked list with 1, 2, 3, 4 as elements. And so what I can do is I can still combine those even further and bind a name v1 to be a link of March, 4. So think about what that does. It shouldn't print anything because we're just assigning it to a statement. But I've made a new link with the first item being March and the rest being 4. So that's totally valid. I can create another link like link of March, link of 4, empty. And I want you to think about how that's different as well. So now when we look at v1, for example, I wonder, how can we get elements from March? Because I know this composition is kind of like saying, I'm putting what March has, link of 1, link of 2, link of 1, link of 2, into here. So if I want to get the number this 2, for example, how do I get there? Spend a moment and think about it. How do I get this 2 March from v1, the first 2? How do I get here from v1? Because we saw that we could compose first and rest to like move around this linked list. So just as like a test, let's think about how we can do that. All right, so let's wrap up our conversations. All right, any ideas? Hands. Can someone help me out here? Can someone start me off? Someone new I haven't called on today. Yeah, what's up?
We're going into March, right?
Yep.
So I would think you could go first of rest of March.
Okay, so what's your name?
Tristan?
Yeah, Tristan thinks we can try first of rest of March. Okay, yeah, so if we start from March, how this will evaluate is, let's think about this. So I have operator, which is the function first, operand, which is a call expression, which means I need to evaluate that operand, right? So if I start from the beginning, I'm going to evaluate this operand, this call expression, rest of March, which will give me not this link of 1, but the link of 2 and onwards. So it'll give me the link of 2 and onwards. And then I call the first of that to give me 1. Or to give me 2, my bad. And so if I wanted to do that same thing from V1, let's say this time I don't want to call it from March, but I still want to reach that same 2, except from V1. How might I compose that? Because we know the way this kind of works is I kind of evaluated this one first, right? So maybe as an exercise, we can try first of V1, see what that gives us. Because first of V1, right, is going to give us March. So maybe if we compose first of V1, now that we know this is like March, we can put that in where we saw March earlier. First of rest of first of V1. Because this is like saying March, right? And so we get that same 2. And so to evaluate this again is, if you want to think about it like the way Python does, operators first, this operand is a call expression, so we have to evaluate it. And to evaluate it, we figure out the operator is rest, and its operand is also a call expression. So really the first one we call is first of V1, which gives us March. And so it works out, because this substitution kind of shows us that it does end up being the same thing when we evaluate it. Yeah, question?
What happens if you were to just type first of V1? Will it say March or
Great question. What's your name?
Drew?
Drew asked what happens if I type first of V1. Let's see. It shows us the abstraction, the kind of what's underneath this. So we'll talk about more about what this list represents in the next couple slides. So it's kind of like a hint for what's coming up next. So let me pull up the slides again. So we've seen we can do a lot of cool things with linked lists. Kind of inconvenient, but we'll kind of see why later. So as another exercise, here's the same code again. I have March 4, V2. And now my question is, which one of these 5 expressions evaluates to 3? Spend a moment, think about it, talk with the people next to you. First rest. Wrap up your conversations in the next 10, 15 seconds and we'll take a vote. All right, get ready to put your hands up. Put the number of fingers for which one you think is right. 1, 2, 3, 4, 5. Oh, wow, that's a lot. Cool. I think most of us are 1, which I think is the right answer. So the way we can evaluate this is I have a slide ready. So if it's 1, it's first, rest, rest, first, rest. First, rest, rest, first, rest. Here we go. First, rest, rest, first, rest, V2. Let's see what happens. So I'm going to create my list for V2. And the thing I want you to think about is like this. Think about the length of that sequence. Think about this length of this sequence. I'm calling link twice, which means I'm going to have 2 links. I'm going to have 2 links terminated with empty at the end. So think about the sequence. And then when I put March inside of it, it's like I'm making a separate sequence. And what I'll do is I'll say March. There's like kind of like an invisible arrow to March. Let's assign that to this first. And I can do the same for 4. I can create a new list for 4. I can assign that list to, I can assign the first of this to be that list. All right. And so the way we evaluate this expression is we kind of go, start from the beginning. Operator is that, which is a function. And this is a call expression, so an operator again. Call expression, so operator again. Call expression, so operator again. It's like we sweep inside using the operator evaluation rule, and then operand, and then apply. We sweep inside all the way to the innermost statement, the innermost expression, my bad. We evaluate the operator of that, which is rest. And so really the first one we're going to do is think about what the rest of V2 is. So V2 we know is a reference, a pointer to this link right here. So when we call rest of V2, what we'll get is we'll say this is V2, and the rest is a little arrow to this link. So rest of V2 is really this link right here. So rest of V2 is an arrow to the next link. I want you to remember that. Rest of V2 is an arrow to the next link. And so if my goal now is to evaluate first of rest of V2, now that we figured out rest of V2 is that, well, first of rest of V2 says, look in the first box, and it is an arrow to this link. So the first of rest of V2 is an arrow to 4. And so we can kind of keep on repeating this procedure, following the rest of this one to be 2, this link of 2, the rest of that being the link of 3, and the first of that link being the number 3. And so that's how we evaluate this expression. Questions about this example? This one's kind of, it's pretty important. All right, cool. So we've seen the abstraction. We've seen that we could define some constructors and selectors. And what was your name again? Drew. Yeah, Drew kind of showed us like a little hint of the implementation. So here's the implementation officially. We saw that there were brackets earlier, so that told us something about the nature of this implementation. And the way we implement a link is using Python lists. So this kind of feels like a little bit like cheating. But the reason why we do this is because we want to combine values. Lists are a way of putting 2 values or 3 values in one thing. And so same thing here. We can combine values using lists. And so to select the first of that list, I can get s at 0 or s at 1. And so this provides the implementation for the constructors and the selectors that we saw earlier. And I really just use Python lists to kind of associate 2 values with each other in one unit. And then to get the first value out of that, I index at index 0. To get the rest, I can index at index 1. All right. So we've kind of seen both the abstraction, how they're implemented, and we've kind of worked with linked lists a little bit. So I want to show you how they are sequences as well. I can get the length of a linked list by writing an iterative program that starts from the beginning at s, with the length being 0, and while we haven't reached the empty at the very end, right? While we haven't gone to the end, I can move to the next link using rest of s, and increment the length by 1 to keep track of how far I've gone. And so at the very end, when I finally hit S, being empty, then I can just return the length at the end of that list. So this should give me the length of a linked list. And likewise, we can define a function getItem, which works similarly to how we define indexing on regular Python lists. So we can start by giving you a linked list S and an index I. And what we'll do is we'll loop down until we hit that index. So let's think about it this way. As an example, let's suppose my I is 0. So I want to get the very beginning element. So if I is 0, this is no longer true. I is not greater than 0. So we don't even execute the while loop and we go first of s, which turns out to be exactly what we wanted, right? We wanted to begin with that linked list. Now if I is 1, we go in the loop, we say rest of s. So now we're moving on to that 1th element. And we decrement I by 1. Now I is 0. When we go to check the condition again, right? We loop, check the condition, I is 0. So we don't execute the body. We exit and return the first of the rest of s, which is the 1th element. All right, so my question for you is try to write a recursive implementation of length link and get item link. So len link takes in 1 argument, which is the link, and get item link takes in 2 arguments, the link itself and an index. Your job is to write a quick recursive implementation that will do the same thing we saw earlier. All right, take out a pen and paper and go. So here's the behavior for your reference. All right, another minute or so to think about it. All right, ready? Yes, ready to come back. Okay, here we go. So our task was to write a recursive implementation of len link and get item link. So length of the link should give us the length of the link, and get item link should give us an item at the index specified. All right, so here we've seen that we can use a little bit of recursion right here. So to get the length of the link, if you think about it this way, let's suppose our link is empty. The link we want to solve is length of the empty link is just 0. And now suppose we have a slightly larger problem. Let's say we want to find the length of length 1. So just like a link of 1, for example, in empty. So link of 1 in empty might say, so I'm going to use a recursive case which says 1 plus a recursive call to the rest, and that recursive call to the rest will just hit the base case, 0, right? So when I return from the 0, I say 1 plus the length of empty, which is 0. So I get 1, which gives me the length of link of 1. And so likewise, I can keep on defining my length of link to work correctly for link of length 2, length 3, and so forth. And it kind of works the same way for get item. I essentially want to recurse down until I hit the position I want. So say I want to get the very first one, I can just return first of S. Otherwise, I'm going to have to recurse down using the rest of S. So it's like a common pattern. We usually want to get somewhere by calling rest of S. And we can reduce our index by 1 because we're getting closer and closer to our target position. So if I start at like index 5, I'm going to use this recursive case calling rest about 5 times. Questions about this recursive code? It's the first time we've seen recursion with linked lists. This will be a big idea on the exam as well. Yes? Great question. So Chuck's question was, what happens if the index is out of range? So suppose we're thinking about get item. Let's say my list just contains empty, for example. Like the simplest case is my input list S is empty, and my index is like index 1 for maybe. So in that case, we would say, I'm not the base case, so let's call rest on S. But the rest of empty, right? Rest of empty doesn't really make sense. So then that's where we get error. When we say rest of empty, there is no for the empty link. Because if you think about what the empty link looks like, is we can show you the implementation, but the empty link looks like this. You can't call first or rest on the empty link. Great question. Okay, any other questions? Yeah.
Is there a difference between rest of S and S of 1? Could you say return 1 plus length list of S of 1?
Yeah, great question. What's your name?
Jack.
Yeah, so Jack's question was, what's the difference between saying like rest of S versus S of index 1, right? And so that's kind of a question of what we saw from last lecture, which is asking us, well, we've seen that the way linked lists are implemented is we use this code, where underneath that linked list is a Python list. And so I could just substitute rest of S to be S of 1, and that code would still work, yes. But the problem with this is that if we later change the implementation for linked lists, we lose this abstraction. Any code that we write using S of 1 kind of like inherently implies that the way the linked list is structured is like that. But because we add another level of abstraction, we add these constructors and selectors, because we can call link, because we can call first, because we can call rest, because we have these extra functions, this allows us to change our implementation. So later in the lecture, we'll show you some different implementations of linked lists that don't rely on Python lists. So kind of the point we want to make here is that, sure, you can substitute rest of S with S of 1, but that breaks the abstraction barrier, and that will be all, basically. It will still work, but it breaks abstraction barriers. And that makes your code very easy to break later on and hard to change. Does that address your question? Cool. Okay, so moving on. It's break time. Take a break. Let's play some music. All right, let's get started. Back from break and back to content. So working with linked lists, we've seen that sequences can be used as containers. And what that means is here, I can ask whether element is in the sequence S. So here's like a short snippet of code, which is based on something we've seen before. I can loop through for each element X in the list S, in the Python list S. I can check if X is equal to element, and I found that element. So I say it's in the list S. Otherwise, if I go through the entire loop, if I try every single item, then I know when I exit that loop, there are no more elements in the list to try. So then I can return false and say it's not in the list. So likewise, we can define lists as containers, linked lists as containers as well. You kind of want to use that same idea. I can loop down through the sequence and check for each item if I'm equal to it, if I'm equal to it. And we can see the same kind of definition. If I reach the end, kind of like at the end of that for loop, if I reach the end of the list, then I know I have no more things. So I know that for sure I don't have this element. Otherwise, if I find a match somewhere in between, if I find a match, then I can return true because I know that I found that match. I contain the element. Otherwise, in the general case, if I don't find it right now, but there are still more things to check, I can keep on looping down by calling rest of s. All right. So the question is, why use linked list if Python lists can do more or less everything linked lists can do? And linked lists are kind of painful because you have to type LINK, open parentheses, and then start putting your arguments. So we've kind of seen essentially this past lecture has been linked lists are so painful, and now we'll see why we care. So we've seen before the counting partitions problem. It looks something like this. I have a base case that is what happens when I'm successful. When I've reached a successful combination, when n is 0, or the number of chocolate pieces I don't have any more. When I don't have any more chocolate, I can return 1 and say, I found a valid combination, because I've used up all of my chocolate. That's like saying I found that valid combination. In the other cases, I say, if I'm less than 0, then I've used too much chocolate. I tried to use too much chocolate. So then in that case, I return 0 to say I failed for that case. And same thing with m. If I try to reduce my partition size, the number of pieces of chocolate I can give out, to 0, if I reduce that to 0, then I found a failure case as well, because I can't try to make any more pieces of, any more like subdivisions with 0. So then in the recursive case, we essentially do the with m and without m case, which is where I try to use however many pieces I'm at right now, and without m, which says try a different number of pieces, try one fewer number of pieces. So the with m actually takes out from my total because I said I've given you this many pieces. The without m says keep the total the same, but try a different combination. But let's say, what if our problem is enumerating partitions? What if I want something better than that? So let's take a look at a demo. I think I need to increase the size of this so people can see in the back. Maybe that's pretty big. Is that good? Good. Okay, cool. So what if I want a better program? What if I want to print the actual combinations? I'm not satisfied with just getting the number of combinations. I want to see what those combinations are. Oh gosh, name error, use m not defined. Let's fix that. So let me fix that real quick. I have a bug in my code. Use m with m. Okay, so if we try that again, moment of truth. Print partition 6, 4. I want to see the combinations I get. And there we go. Those are all the combinations. So how can we do this with just numbers? Well, we saw with count partitions, it's kind of hard. Because when you only store one bit of information, when you only store a single number, and that number is the only thing that's passed back to you, it's hard to do more than I don't know, maybe we can try to use strings instead, but it's tricky. So what's nice about the link abstraction is that it makes solving this problem a lot more elegant than trying to force it in with numbers or just strings alone. So let's take a look at how we can achieve this effect, how we can make this happen. So here I have enumerating partitions. So before we tried to count the number of partitions, now we're trying to print them out. All right, so it starts like this. I define a function partitions, and it works the same way. I just have n, the number of pieces of chocolate I have right now, and m, which defines the largest number of pieces I can give to someone. So here's n, the number of pieces I have. M is the most I can give out right now. So I have kind of that same idea. I have a base for success, right? Which is to say, return link of empty, empty. And we'll kind of revisit why this is important. But for now, just think of it as a success case. And then here I've combined the failure case. Before we had 2 failure cases, now we're just going to squish them in 1. And here we return empty. We'll kind of see why later. And if we jump to the recursive case, we still have that same set of recursive calls. We have one strategy which says, let me try to use the pieces I have right now, and one which says, let me try to find a different combination using a different number of pieces. And here we're going to define a function add m, which takes in a linked list, and what it'll do is it'll add m, which is my current partition. So this will kind of give you some, I think what should be running through your head right now is like, how will I use this function add m? How can I use it to compose something big? And so here's kind of like the key. I'm going to map link add m and with m. And we'll talk about what that does here. But this will kind of give you some intuition for how with m will be changed by add m. At the very end, we combine the results. So this is like doing with m plus without m. So to break that down again, we have a success case. We have a failure case. We have the same recursive calls here, but kind of the key difference is how we solve the problem. There's an additional step we have to do when we combine the results. So we have the base cases, have the recursive cases, but when we're combining the results, we have to do extra work. So the problem is solved by adding one link at a time. And it's kind of like the same kind of pattern that we saw with counting partitions, where we just added the numbers up. But now since we're working with linked lists, we want to say, like let's say we hit that base case of saying, I found some kind of valid combination. When I step back from the base case, when I return from that base case, I want to say 1 plus that 0, for example. 1 plus that 0. So that's kind of add m's job here. I'm adding that m that I use. And then what we do with maplink is, how it works is it applies add m to each link in with m. So the way we define maplink is it applies the function, this one, to every element in with m. So with m is some kind of linked list. Add m is a function that takes in one argument. And maplink applies add m to each item in with m. And so this is kind of where these base cases get important. So suppose I've hit the failure case, right? So suppose I've hit this to get all the way down to the failure case. Now the question is, what happens when I return back up? Since I know that this is a failure case, I don't want to combine my current m, the person who called that failure case, with it, because I know that I probably use, maybe I use too much. Maybe I use too much chocolate. So I don't want this to be a valid combination. So the way with m, the way we combine that is that when we call maplink using add m on this bad combination, the way maplink works is that it doesn't apply it onto the empty list. So if I get an empty link like this, maplink will say, let me just skip over it. I don't care about it because it's not part of the link. It's because I'm done, right? When I get an empty list, there's nothing else to apply onto it. There's nothing to apply to that empty list. Does that make sense? Wait. This moment's kind of important. This is kind of a crucial point. When I try to map the function add onto empty, there's nothing to map onto it, right? Because it's empty. There's nothing. There's no values. So the key distinction with the successful case is that now this is kind of like a weird bit of code, but what it's saying is I have a link with the empty partition to build off of. Because here, this empty is part of saying I'm done with the list, right? But this empty here is saying that this is my value. This is my value. This is my first. This empty here is important because it says that I'm going to build off of this empty. Now I have a link of one thing, and that one thing is empty. This is kind of weird. I have a link of one thing, and that one thing is empty. So when I call map link on this link of one thing, it's going to apply the add m function, which just links the number that I used with the input it gets, which is empty. So now when I call that, when I go back from the successful case, when I try to map link, what will happen is I'll add my first number with a link of empty, and now I have a link of one thing. I have one valid combination. So I really want you to think about this. Think about how the diagram looks like in your head. And the very end, once we have all the results, we can combine them with a function like extend. So extend is like the plus sign here. It's just taking these two linked lists and combining them together. Because I get some number of combinations from with m, some number from without m, and when I combine those combinations, then I'll get my total result. Questions about this? Do you want me to show you something else about this? Because this is definitely I think a very challenging concept. So I want you to think about how it relates to counting partitions, because that's kind of where we start. And think especially about how these base cases are important. And so the way MapLink works is that if I hit the empty, then there's nothing to add to it, whereas this has a link of 1. Yeah, Ron.
I'm completely having trouble visualizing what with them is holding after that link.
What with M is holding after MapLink? Okay, yeah, let me actually draw a picture. I think that'd be useful. Let me pull up my picture drawing app. This will be an exciting detour. If it loads. Okay. All right. Oh no, let's not flash. Maybe I can do like this. All right. So let's try to draw a new node. So I guess a good place to start is to contrast these two base cases. How are they different, right? So let me draw that out for you. This is going to be slightly awkwardly scribbly. But empty looks like this, right? It's like a square, and I put an X through it. That's empty. It's pretty awkward, but it's empty. This is empty, right? This is the bad case. And what MapLink does with this empty case is it says, I have a linked list with nothing in it. Right? This is a linked list that doesn't have anything. This is the empty linked list. I don't have anything. So there's nothing to apply onto it. So it stays empty. It stays an invalid combination. Now the difference with the successful case is I have link of empty comma empty, right? And so when I call the link function, the link constructor, what I'll get is a 2-element box like this, right? Oh, let's not make it that high. Here we go. MS Paint mode. Close enough. All right, so remember, when we call link, we get something that looks more like this. And what we put in that link, right, is we put empty comma empty. So that looks like something like this, where the first element is empty. Right? First element is empty, and the rest is also empty. And this is, oh my gosh, this takes so long to draw. Almost there. All right, that's empty, right? So notice the difference. This is a totally different structure. And so what MapLink sees is that it sees, I have a link of 1 item. And that 1 item here is the empty link. And so remember the way MapLink works is that it applies the addM function to each link in this list. So now I have a link of 1 thing. So when I call addM on this 1 thing, let's say we're calling like maybe addM, like maybe I want to link 2 to it. What I'll get is I'll get this, no longer this structure anymore. Not that, oops, that's kind of long. Not this structure. We won't get this structure anymore. We'll link, because that's what addM does, we'll link my, oh gosh, here's the hard part, M. It's pretty good. With this empty. And now I've created 1 valid combination. This is the way I want you to visualize it. When addM runs, I get this structure, and then MapLink puts that into, essentially does that job. Does that help clarify? Yeah, so this is what goes on, but I think it kind of relies on your understanding of count partitions. So if this is still confusing, I recommend going back to count partitions, thinking about those base cases, seeing how these base cases relate, and then thinking about this picture. Because what MapLink does is goes through each element, there's only 1 element here, and it applies addM to this empty. And so it kind of builds off of that. So if we think 1 step further, if we then go back to the person who called that one, we'll call addM on that again, and we'll get a new link in front of that. So we'll be recursively constructing it 1 link at a time. All right, Sam, do you have something to show off?
I will have a picture over here. I assume it's easier to draw on the chalkboard. You guys can come up here after lecture. That's it.
All right.
You can still pay attention to Kevin, but I'll just be working here by myself.
Okay, so we've seen how we can use the 2 base cases together with MapLink. And so we take that image and we just keep on adding more links 1 by 1. Okay. After that, we're going to talk about alternative implementations. Or are there any last other questions about this first before we move on? Yeah.
Hi, so you're saying that it's really a lot easier to use this than to use lists or partitions?
Yeah, great question. What's your name?
Tom.
Sorry?
Tom.
Tom, yeah. So Tom's question is, it's easier to do this than with Python lists?
Well, are you saying because you're saying that it's a lot easier to use linked lists or partitions other than lists, so does that mean that using partition for lists is going to be super complicated? What's that going to look like?
I guess the problem with partitions on lists is that they're different syntactically. You're going to be using brackets, right, to define your lists, but we still have the same ideas going on. We need some way to define no combinations versus some way to define a combination that I want to build off of. So I think we can still define it analogously, like maybe a list of an empty list. That would be one way to think about it. But the nice thing about linked lists is that it has a nice syntax that lets you link it up one by one. So whereas here you might have to do plussing and doing some tricky stuff with maybe going inside and plussing. We have these convenient functions that allow us to work together with it without having to think too much about the nested list structure. Does that kind of make sense? I think the nice thing about this is that we don't have to think so much about all the nested levels in a Python list. So I think that's the main elegant part of this. But you can definitely solve the same problem using Python as well. Great question. Awesome. All right, so moving on, let's talk about alternative implementations. So we've seen that we can already implement linked lists using Python lists. Let's see a new one. Let's say I define my constructor, define a link function, and we go straight into higher order functions. So I'm going to define a function dispatch that takes in a message. And what it'll do is it'll ask if that message is the first. What it'll do is it'll look up the first in its parent frame. So kind of the way we want to think about this is that I'm storing my information in the link frame, and when I retrieve it, I can retrieve it through this patch function. So this is going to look up the first in my link frame. And same way with the rest. I can define it to return rest, and that'll look up the link frame as well. This is where our knowledge from higher order functions come in handy. And so at the very end, we return dispatch, which will essentially figure out how to interact with this structure. So we can define our two selectors, first and s, kind of using that dispatch idea. So given an s, which is really a dispatch function, I can call dispatch with the message first, which will go in here and ask if the message is first, return the first that I kind of stored in my parent frame. So it's kind of a neat idea is that we can use the frame structure in Python as a storage device. We can say I can store names, value bindings within my parent frames and use that to look up information. And I can create arbitrarily many things I want. Right? I can create essentially sequences of however much stuff I want to put in there using this structure. And so if we take a look at how that evaluates, just want to take a couple steps. Things here. Yeah. Let's take a couple steps through this code. I provided some of the code here. So we defined the empty link to be just x. So this is like an arbitrary definition. This is our link constructor that we saw from before, the dispatch function. And these are the selectors that we saw from the slide as well. And so if I want to create a link, I can step through, define my functions. And when I create my link, what I'll do is I'll call my link constructor, passing in world and rest, world and x as my rest. So that's because, here we go, because we evaluate this nested call first. So when I evaluate this nested call first, I create a new frame with world and empty. And so when I go back to evaluating the code here, what I'll do is I'll define a dispatch function, return that dispatch function, and now when I create the link for hello, with the rest being the dispatch from for world, if we go through our code again, we'll see that we define a dispatch function, just the same. But the important thing to notice here is that these two dispatch functions have different parent frames. So this is how we distinguish between my first element and my second element, is that because they have different parent frames, when I look up, for example, the first from the outside, from the first one, I'll get hello. Whereas if I look up first from this dispatch, I'll look in its parent F1 and get world instead. That's kind of the idea we want to think about here. Is when I define this dispatch, it works like that, because it has different parent frames. And so where I turn it to the outside world, I bind hello world to this beginning of the list. And so if I want to ask the question, what's the first and the rest of hello world? We end up calling rest of S first. So I open a new frame for rest. And what we'll do is we'll call that dispatch function with rest as the argument. So when I call rest, I open up the dispatch function, my message is rest, and my parent is F2. So when I try to look up the parent, it'll go, let's use this one. And it'll say, go to the dispatch function with the parent being F1. So it's like a useful example to kind of roll over on your own time. Just kind of try to figure out how we can use this as a storage device. All right, any questions about this structure? All right, otherwise, we can see that I could define my dispatch in really any arbitrary way. I could say, well, what if my message was Kevin? I could still return the first. So really the choice of strings here doesn't really matter as long as my constructors and selectors are in sync, as long as they both agree. I can change my implementation up however I want. And what's even better is that I can change my list implementation directly to this higher order function just by changing the constructor and selectors. So to address the earlier question I had about why do we care about using rest of S instead of S of 1, because we can do stuff like this. We can change our implementation, we can add extra information, and our code will still work the same because we have this extra level of abstraction, this abstraction barrier. So I think it's, we can add more information or change our implementation. All right, otherwise, summary. So we've learned so far that linked lists are a type of sequence abstraction. They're an implementation of a sequence. And we see that linked lists are composed of two parts. They have a first, which is the current value of the link, and a rest, which is the next link in the list, which might also be empty. And we've seen that data abstraction means that implementation details of the first and rest selectors are not necessary. So that was just the past couple slides about alternative implementations. And we've seen, I think this is the most important part, that we have two views of linked lists. This is from way back in the beginning of this lecture. We saw that we can think of linked lists by their individual links. Those rectangles of two items, right? A first and a rest, a first and a rest. And that's what Python sees. They see the individual links. But it might also help to think of them as in terms of the entire sequence or the entire linked list as a single unit, because that helps us reason about recursive programs. So I want you to remember that there are two ways to view this. Your TAs might use them kind of interchangeably. So make sure that you're always aware of which one we're talking about. I think having both of these views is really useful. All right, otherwise, thank you so much. Have a great day. Go to lab.